Welcome back, folks, on our video lesson for area of regular polygons. We're going to use make this third video to use special right triangles and trigonometry in finding the area of a regular pentagon. So what we've already covered, if you haven't watched these yet, please do watch these videos. We talked about some new concepts with regular polygons and our good friend, the Apothem. We talked about how is it that we can find the area of a regular pentagon or a regular polygon with our new formula that the area is 1/2 the apothem times the perimeter. And we mentioned briefly, but now we're going to really dig in, how we can use trigonometry and right triangles to work with area. So that's what we're going to do right now. Okay, we're going to recall some of our right triangle stuff, and we'll get some examples going. So let's use some special triangles. Here's a question. We have a honeycomb is made up of regular hexagonal cells. A hexagon has 6 sides. Okay, and since they're regular, they're all the same distance. Okay, so each side is congruent. So we have 6 hexagonal cells. The length of a side of a cell is 3 millimeters. What is the area? Okay, so this is all we have. So we got to start thinking now. Well, first thing we'll think about is drawing a picture. If you want to, draw a picture. We have our hexagon, right? So 6 sides, 1, 2, 3, 4, 5, 6. So our regular hexagon, and each side is 3 millimeters. Okay? So now we got to think. How do we find the area again? What's the area of a cell? So remember what we had learned in the previous video. The area is 1/2 the apothem times the perimeter. So we have to remember that area is 1/2 the apothem times the perimeter. So what are we given in this? We're given none of the above. We don't have the apothem and we don't have the perimeter. But what can we find? So the first thing we can find, I hope you see fairly simply, is the perimeter. The perimeter is going to be found with our regular hexagon, 6 sides, times 3 millimeters each. So our perimeter is 18 millimeters. So we know the perimeter is 18 millimeters. The only question now is the apothem. So how does our apothem work? Remember, it goes from the center to a side. Okay, so this is our apothem, from the center to a side. And if you recall from previous notes, what does the apothem do? The apothem bisects the vertex angle, and it also bisects the side of the regular polygon. So we didn't quite use this yet, but we're about to. The apothem bisects the side of a regular pentagon. So what we have just now created is a right triangle. Now here's what's interesting. With this right triangle, we have a neat thing about to happen. So we have a little right triangle that happens here. And what I'm going to do is a little pop-out magic. If the entire side length is 3 millimeters, what will be the short leg of the right triangle? Just the short leg is going to be 1.5 because the apothem bisects it. Okay? The apothem bisects it. So let's draw a little triangle. Beep, boop. We know we have the apothem that bisects our side. So we have a right triangle that pops out here. The only question is, we're still looking for whatever the apothem is. How are we going to find out what the apothem is? So here's the neat thing. It would be helpful if we knew one of two things. It'd be helpful if we knew what the radius was, or if we knew what the angle was. Now, can we find out what either one is? We can't find the radius, that's nothing's given, but we can find the angle. How can we find the angle? Remember how the diagram works. We have a vertex angle, and we find the vertex angle from dividing the number of sides into 360. We have the vertex angle, and then the apothem cuts that vertex angle in half. So what am I talking about? So in our hexagon, we have, well, 6 congruent triangles. These are each congruent. Each of these triangles has a vertex angle. Okay, and that vertex angle is going to be 360 divided by 6 because it's a hexagon. Now that vertex angle is going to be 60 degrees. Okay, so hopefully you understood what just happened. That's a lot of math right there. There were 6 triangles from the hexagon. The vertex angle would be 60 degrees. Okay, now again, what we remember, the apothem bisects the vertex angle. So if the apothem is bisecting the vertex angle, and the vertex angle is 60, then what does that mean for this little angle right in here? So this little angle right in here is 30 degrees. Now that is a neat thing, because what do we have now? We now have our special right triangle with a 30, 60, 90 triangle. So all of that comes into play. Okay, all of that comes into play. So now we have our 30, 60, 90 triangle. We have a short leg. The apothem then is the long leg. And how do we find out the apothem then? It's going to be the short leg times the square root of 3. Okay, so we have our short leg times the square root of 3, and that is our apothem. So when we use our formula, the area of the regular pentagon being 1/2 times the apothem times the perimeter. Okay, so we have to remember how that happened, and I'll review in a second. The rest is calculator work. So let's throw it all into the calculator. So we have, let's see, 1.5 times 18 times the square root of 3 equaling, and then we're going to divide that by 2. And so we have our area of 23.4, let's say, square millimeters. Okay, so 23.4 square millimeters. And so we find our area that way. So what just happened? We have to think about this, okay? Well, we have a couple of regular polygons that would have radii that make special right triangles. Okay, and that's just what happened here. Remember, we had a radius here and the apothem here, and we ended up making a special right triangle. Why? Because we have to remember about vertex angles. So what just happened? In a triangle, in a regular triangle, did you know that we would end up with vertex angles, apothems, and radii that have a 30, 60, 90 triangle? A square, there's a 45, 45, 90 right triangle, and a hexagon gives us a 30, 60, 90 triangle. That is a neat thing to hopefully you can pick that up. Okay? So that's just what happened here. We have to remember all of this stuff that just came into play. So we've got to remember these big notes. Let's do some more examples, and then hopefully that'll come into play. I'll keep this handy, and as should you. All right, so here, one last question. We'll call it a day. The question now is, what is the length of the apothem of a regular hexagon with 10 centimeter sides? If necessary, round to nearest tenth. Well, this isn't an area question. It's all about a regular hexagon. The question is find the length of the apothem. So again, if we have a regular hexagon, okay, we have a regular hexagon, the apothem goes from the center to a side, okay? But the apothem is inside of a vertex angle. Remember, the apothem bisects a vertex angle. Okay, so that's just what happened. We have to recall all of these notes from everything that we had learned in the unit. Okay, funny enough, this is a regular hexagon. Okay, so all the notes come into play. Vocabulary is pretty huge. So what's the length of the apothem? We're looking for A. Now the 10 centimeter sides go all the way across 10 centimeters. Oops. So this is 10 centimeters. That means if we're to isolate just one of these triangles, if we were to isolate it, remember what the vertex angle would be. So the vertex angle would be in here, and the vertex angle is going to be 360 divided by hexagon is 6, so it's going to be 60 degrees. So this vertex angle is 60 degrees. What does that have to do with this little right triangle in here that makes it a 30-degree triangle? So let's pop that right triangle out, and we'll see what happens. So the vertex angle is 60. That means the angle in this triangle when we pop it out is 30 degrees. So now we have a 30, 60, 90 triangle. Okay, so we have a hexagon that would make a 30, 60, 90 special right triangle. The question is, what is the length of the apothem, right? So we're going to look for the length of the apothem. How are we going to find it? Well, what is the length of this side? All the way across is 10, but we know that the apothem bisects the side of the regular polygon, so this little short leg here is half of 10, or 5. Okay, so that makes the short leg 5, and as we know from our 30, 60, 90 triangle, the short leg is half the hypotenuse, and the long leg is the short leg times the square root of 3. So the long leg in this case is the apothem, or 5 times the square root of 3. Okay, so we have our long leg, 5 times the square root of 3. That's the apothem. Or the question says to round it to the nearest tenth. So we do 5 times 3, 5 times 3 square root equals 8.66, or 8.7. So 8.7 centimeters is the length of our apothem rounded to the nearest tenth. All this we have to know. Now, here's another question. What if instead of saying regular hexagon, the question was about an equilateral triangle? So what if the question was about an equilateral triangle? Can we find the apothem of an equilateral triangle, bloop, that has the side length of 10? And the answer is yes, we can. Because look at what's going to happen. In this equilateral triangle with our side length of 10, we got to know what the vertex angles are. So here's a triangle. Here's a triangle. We have 3 vertex angles. Each of the vertex angles is going to be 120 degrees. Okay, so each of the vertex angles is going to be 120 degrees. That means right in this big triangle, that's 120 there. So if the apothem bisects the vertex angle, that means in our little pop-out triangle that we're going to make, bloop, 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 that means in the little pop-out triangle, this angle in here is going to be half of 120, or 60 degrees. So another 30, 60, 90 triangle. Okay? But in this case, the side length was 10, but the apothem bisects the side. So now the short leg, well, actually the long leg in this case, we got to be careful with how we're drawing the picture. Look at how I drew this picture. The long leg is going to be 5. So I should probably redraw this picture, right? Because that's what's happening. This is more accurate, 60, 30, and 5. Okay, so you got to see what's happening with numbers and all that stuff. So the long leg is 5. That means the apothem, or A, is 5 over the square root of 3. Or 5 times the square root of 3 over 3. If you didn't understand what just happened there, that means you've missed a lot of stuff from chapter 8. So go back to chapter 8 here. Chapter 8. Whoop. Okay, so we got to remember 5 times square root of 3 over 3. Or if we're rounding, right? We're rounding anyway. We can just stop right there. 5 divided by 3 square root equals 2.88, or 2.9. So in this case, it would be 2.9 centimeters would be the length of the apothem here. And the question was also the same for what if it was a square? So we make a square. Square is a regular polygon. Okay, so we have a square here, and from the center, an apothem, and vertex angles. So in a vertex angle for a square, we're dealing with 360 divided by how many? 4. That means we have 90-degree vertex angles. We should know that already. 90-degree vertex angles. And in our pop-out triangle, when we're looking for the apothem, we pop out our triangle. Here's our apothem. That means this angle is going to be 45 degrees, half of 90. So here we have a 45, 45, 90 right triangle. But remember, the side length was 10. All the way across was 10. So just this side here is going to be half of 10, or 5. That means our apothem is also 5. Okay, so we have, centimeters in this case. So we have to remember to navigate our way around stuff. And that is it for the area of regular polygons. So we got to remember our notes for this. The formula for the area, 1/2 the apothem times perimeter, and navigating right triangles. Did we use trig in this one? Not yet, but hang on tight, we will. This will be back. All right, thank you guys very much. Enjoy.